In this video, we're going to learn how to simplify a quotient of radical expressions. Now, if two radical expressions are real numbers and they're being divided, as long as b does not equal 0, you can combine them into one radical. And again, they need to be real numbers for you to do this. Now, for each example, we're going to divide and simplify. We're also going to rationalize the denominator of each expression, which I'll get into later once we need to do it, and use absolute value symbols when needed. So again, we'll start with this first example. We'll see here we have 18x to the fifth, the square root of 18x to the fifth, divided by the square roots of 2x to the third. Now these are odd powers underneath an even radical. It's a index of 2. So x to the fifth could be a negative number if x is negative. But in order to keep this a real expression, we're going to state that x must be greater than or equal to 0. This will help us avoid using absolute value symbols as well, if I'm also assuming that x has to be positive. So since they have the same degree, and I'm keeping x greater than 0 to keep them real, I can combine these into one radical. So I'll have 18x to the fifth divided by 2x to the third. And now I have the 18 divided by 2, which is 9. And then x to the fifth divided by x to the third. So that's 5 minus 3, x to the second. And now I can finish simplifying. 9 is 3 squared, so the square root of 9 is 3. And the square root of x squared normally would be the absolute value of x. But since I'm already assuming x is positive, I can just write this as 3x. The absolute value is redundant once I'm assuming that x needs to be positive. For the next example, I'll have cubed roots. In this case, I do not need to worry about absolute value, so I'm not going to even put like that y has to be greater than or equal to 0, because y can be negative, and you can still take the cube root of it. So here they have the same index, so I can combine them into one big cube root, giving me the cube root of 162 y to the fifth over 3y squared. Now, I have to divide 162 by 3, which should be 54. So I have the cube root of 54. And then y to the fifth divided by y squared, 5 minus 2 gives me y cubed. And now 54 is not a perfect cube, but I can look at its prime factorization to see how I can rewrite that to find a perfect cube. So 54 can be written as 6 times 9. 6 can be 2 times 3. Those are both prime numbers. And 9 is 3 times 3, so we get 2 more prime numbers. So I can rewrite 54 as 2 times 3 to the third power. That's going to help me see where a perfect cube is. Because now I see that I have 2 perfect cubes, this 3 and this y. That will cancel out those powers, leaving me with just 3y. But that 2 is only raised to the first, so 3 can't go into that 1. So that's just going to remain inside of the cube roots. So I have 3y cubed roots of 2. For this next example, I have square roots on top of each other. So now I have to worry about if I can get an imaginary number here, because if it's imaginary, I cannot combine them into one. So I see here, x could be negative, and it's not being raised to a power. So it could be positive or negative. So I need to assure that x is greater than or equal to 0. And I can also see that y squared is always positive, so I don't need to worry about that. But since y cubed could be negative and it's underneath the square root, I also should assume that y is also greater than or equal to 0. So here I will not need to use absolute value symbols since I'm already assuming that those variables need to be positive. But now that I'm assuming them to be positive, I can combine these two over one radical, and I'll have 3xy squared divided by 5xy cubed. And 3 over 5 doesn't simplify any further, so I have to just keep one in the numerator and one in the denominator. The x's cancel, And then y squared divided by y cubed will leave me with 1y in my denominator. So now, rationalizing the denominator happens when there's still a fraction left over in a radical, or there's still a radical in the denominator. So we're going to rewrite the expression so that there are no radicals in the denominator or any denominators inside of a radical, like we have here. So if I separate this back again to the square root of 3 over the square root of 5y, I now want to rewrite this so that there's no radical in my denominator. The way to make that happen is to multiply by something that would create perfect squares in that radical in the denominator. Right now it's 5 to the first and y to the first. So if I multiply it by 5 and y, that will create 5 squared and y squared. But I can only multiply things if they're both within the same indexed radical. So it needs to be the square root of 5y. But if I multiply to the bottom of my fraction, in order to keep this expression equivalent, it also needs to multiply to the numerator of that fraction. So now when I multiply, my numerator becomes 3 times 5y underneath the radical, so 15y. And again, I'm assuming y to be positive, all over the square root of 5 times 5, which is 25, and y squared. So my final answer is the square root of 15y over the square root of 25, which is 5, and the square root of y squared, which is y. So square root of 15y over 5y. So that's what rationalizing the denominator looks like. It happened at this particular step. I'm just trying to get rid of the radical that would be in the denominator, so there's no longer a radical down there. So whenever you get rid of the radical, it rationalizes that denominator. Now let's look at this next example. I have the cube root of 5x squared over the cube root of 12y squared z. You'll see that they're already separated, but I'm also noticing that 5 and 12, if I were to combine these, wouldn't cancel. And there's no x's in my denominator, nor y's or z's in my numerator. So combining them wouldn't make a lot of sense since nothing would cancel out. So what I'm actually going to do is start to simplify or rationalize this denominator. But before I do so, I'm going to look at what the prime factorization of 12 is to start. So I can see if there are any perfect cubes in 12. Now 12 is 4 times 3, and 4 is 2 times 2. So I end up getting 2 2's and a 3. So 2 squared times 3 is equal to 12. So now I'm looking at the cube roots of 5x squared over the cube root of 2 squared times 3 y squared z. Now none of these factors are perfect cubes. So in order to rationalize, I need to multiply by something that would create that perfect cube for each of those factors. So I need to make this 2 to the third. So in order to make that happen, I'm going to multiply by 2 to the first, but within a cube root so I can combine them. This 3 to the first needs a 3 cubed, so I'll multiply by 3 squared in order to get that 3 cubed. So again, I can take it out of the radical. Like you saw down here, I created those perfect squares to make that happen. Now y squared needs one more y to make y cubed, so I'm going to multiply by y to the first. And then z is just to the first power, so it needs to be multiplied by z squared. Now whatever you do to your denominator, you must also multiply to your numerator in order to keep this expression equivalent. So 2 times 3 squared y z squared. So now multiplying this out, my numerator becomes 2 times 3 squared times 5. That's the coefficients. Then x squared, y, z squared. And none of these are perfect cubes, so nothing can be taken out up there. But in my denominator, I'll have 2 to the third underneath the radical, 3 to the third, y to the third, and z to the third, which is exactly what I was going for. So now that they're all raised to the third power, each of these factors can be factored out of that cube root. So it leaves me with the cube root of 2 times 3 squared times 5, which if I did 2 times 5, that's 10. 3 squared is 9, x squared, y, z squared, all over 2 times 3 times y times z. So my final answer becomes the cube roots of 90 x squared y z squared over 6yz, with that denominator now rationalized from what it was before. You'll notice here I'm not going to use any absolute value or even check that it's positive because cube roots can have negatives in them. And that is how you simplify a quotient of radical expressions.